last time we used Riemannian metric and consider the Riemannian geometry, and from here we just introduce a notion of length, and also between 2 points. And also we introduce so-called Hodge cell. And at the end of the day, so we just consider Hodge decomposition, Hodge theorem, and a Poincare derivative. That's what we have done for Riemannian manifold. So today, so we talk about a bit more about the Riemannian geometry, Riemannian manifold. So today I'm going to talk. So the basic notion of the idea of Riemannian manifold is coming from Riemann, like 1854. This the famous speech at the Get in Germany. And after that, many people has tried to construct the rigorous mathematics of his idea. That's nowadays called Riemannian geometry. And then, based on the Riemannian geometry, Einstein constructed general relativity. So that's what we are going to learn today. So to construct the Riemannian geometry, we need to introduce. So now we introduce the notion of metric, and from here we introduce today so-called connection, and also geodesic, and also curvature. These are most like fundamental concepts in Riemannian geometry. Fundamental concept. That's what we're going to learn. And based on which the Einstein theory of general relativity is constructed. That's what we're going to learn. So given Riemannian geometry, so I'm not going to introduce Riemannian geometry in standard physics ways. I mean, I think Eden is teaching the GR this semester. How many of you taking the GR? Only, huh? This time Eden is teaching GR. Okay. So you're taking. Only a few people are taking this. I don't know why. I mean, you should. Anyway, it's too late. But you should. And how many of you have taken GR? So, many people already taken. Okay. So I'm going to introduce Riemann geometry in not physicist way. Physicists learn Riemann geometry through GR. They start start with the equivalence principles of equivalence and so on, and then they just introduce the notion of curvature metric by physicist way, but no, this goes a bit different, a bit more mathematical way. And then there's some very concise summary of Riemann geometry in Vienna's book in Monster. If you want, part 2. If you want, you can take a look at it. Actually, I'm following his position. Okay, so let's see. So definition. So connection. So connection. So connection is the I call it nabla. It's the map from vector field times vector field goes to vector field, and I use notation x, y, is mapped to delta xy. I will write like this. To satisfy the following condition. So this means we sometimes call covariance derivative. Covariance derivative of vector field of y along x. So that's, I mean, in physicists usually write down. Anyway, I'm going to connect the physicist way of writing covariance derivative later. So just accept now. So now. So it satisfies the following condition. So this is linear in first vector field. This is linear in first vector field. And the second is the additive in this second field, additive in second vector field. Of course, f and h here, f and h are the function on manifold M, and the x, y, z are the vector field. The vector field. Okay. And furthermore, the question, it's natural to ask the question that what if you add as a multiply in some function on the second field. So if you multiply some function in the second vector field, what you get is the Leibniz rule. This is Leibniz rule. So this is linear, additive, and Leibniz rule. And so of course, so this quantity is what? Element of what? So vector field acts on function, and then what you will get is what? Do you remember? Vector field acts on function. What's this element inside? In which set does it belong?
Real number.
Huh?
Real number.
Not real number. So vector, if tangent vector acts on some function, you get the real number. But here it's a vector field. It's a function. Good. So this is function inside a function. The function acts on vector field, so therefore whole quantity is vector. It's an element of vector field. Okay, and also function, and this is vector field, element of vector field. So times function, we get a vector field. So at the end of the day, you get a vector field on the right hand side. So everything what you obtain is vector field. So that's why. So you have if you have a two vector field, you get the nabla assigned another vector field. That's the rule. Okay, so this is the connection, and actually, so note that the so remark is there are many connection, infinite many connection, not unique, that satisfy this condition. In fact, this notion of connection really comes from vector bundle we will learn later. So there are lots of connections, but we will consider a little bit more about the connection that is compatible metric. But before then, let's try to connect to physicist notation. So if you have the manifold with local coordinate 5, which is x1 dot xn, this is a sort of open patch with local coordinate on M, then so on this open patch we have the vector field is something like this way. The basis of the vector field is this one, and with this basis people usually write so if you have a two vector field with the two vector fields, so these are the basis. So you have a manifold, and you have an open patch U, and then now so there is a local coordinate x1 and xn or whatever xn dot dot dot. And then the vector field is bound by partial x, these bases. And then, so of course, these are bases of vector fields, so one can assign the two bases using nabla, and you get another vector field. And since these are bases, span the bases, therefore everything can be written in terms of bases. That's what it means. And here I use already, so here, yeah. I think I used already the Einstein convention. So sum of k is assumed, okay? So I'm not gonna write down sum. So if you have the same indices, it means it's just summation over k, that variable. Okay? And moreover, so therefore, so if you use this rule, so physicists usually write down x is xi, y is in this basis can be written as follows. So you just assign that rule. So you just assign this rule to get the right answer. So if you assign apply the first one, we just get to have this one. Okay, then what you get is xi partial I y j. And I just use second Leibniz rule, no, third Leibniz rule, so that so this is the from here to here you get the Leibniz rule. Number 3, from here to here you get the linearity. So this is how the physicists usually write. Physicists usually write xa, nabla a, yb, whatever, yb. So this is the usual physicist notation. In GR people use, anyway, I should write the I and j maybe. So that is equal to this guy. Oh, I think I made some mistake. I think I made a mistake.
The first term should add partial j.
Yeah, so here I need to add. Yeah, so I need to add j. Yeah, this one is left. Yeah, so yeah. So this one is often called anyway. So another way to define the connection is just introduce so-called So again, so you have a manifold, and you consider curve, the curve gamma, and then you consider the vector field. So of course vector field X is like a vector field whatever, all over the smooth vector field along the all over manifold M. But you can just consider the vector field on this gamma. Okay. So in the lecture note, I just consider gamma is some curve, smooth curve. I is some segment in R, the smooth curve. And then, so J gamma as the vector field along gamma. Then the nabla, given the connection nabla, one can define a covariance derivative ddt, which is a j gamma to j gamma, such that it satisfies the following condition. So the so this is just the second. It corresponds to second condition. Maybe I should use y plus z, maybe. Dy dt plus dz dt, and then have a Leibniz rule. Okay, so this is the, okay, so people are coming. It's early morning. I think you guys are spending significant time last night, I guess, to solve homework. Anyway. So people are coming late. Anyway. So that's how we introduce a covariance derivative. So this is the covariance derivative along gamma t. So, oh, sorry, I didn't mention one thing. So what is the first condition? What are the first condition? What are the compatibility nabla and D? So, and also another condition, let's go 1, maybe 1. I shouldn't, yeah, 0. 0 is dx dt. 0 is the nabla gamma dot 0. So this means as follows. So you can assign so tangent vector at each point of this curve. Okay. So this tangent vector is gamma dot. So this tangent vector gamma dot gamma ddt, as we learned. So tangent vector at the point on a curve is just a derivative of gamma. So therefore, these also can be understood as the element inside a j of gamma. So therefore, so one can just have, so at the point gamma is 0. Maybe let's call it at this point gamma of 0. Is it visible? Blue is not that visible. That's what you guys say. I think I shouldn't use blue. So at this point, gamma equals gamma 0, so let's use orange in that case. And the gamma dot is the tangent vector at the gamma of 0, okay? So one can take covariance derivative. So this is vector field at the point 0, t equals 0, that assign the axon x. Oh my goodness, did I? Okay, yeah. So that can act on x. That's a definition at the point gamma equals 0. So if you even if you change t, you can define the dt. Point t is equal to s is just nabla gamma dot s x. So that's how you define the covariance derivative on this vector field. So in other words, if you use tangent vector along curve to take covariance derivative along x, okay. Maybe I should. It's too late to change, but I should use y instead of x. But you can change your notation on your own. And if you use local coordinate, so ddt, dx, dt, this covariance derivative can be written as, you can easily see dxi partial I ddt. So therefore, you can apply first this Leibniz rule over there, so that you have dxi dt and plus dx. Oh, I think I should be careful about this is capital X, d capital X dt I plus dxk. So this is the small x for coordinate, local coordinate, and then capital X j gamma jk or kj and I. So that's the if you apply the rule over there, what you get is this one. Okay. So here you just have the first one you get the Leibniz rule. The second one you just have this part is the same as xi. Yeah, I think maybe I should use anyway. I think it's okay. Yeah. So xj, d partial I dt is just you just apply xj nabla dxi dt partial. Sorry, I should use k acts on I. So this is equal to xj gamma k j I partial. That's what's going to happen. I think, sorry, so this should be j, sorry. J. And that's second term you obtain. Oh my goodness, I think I should put another one. You should correct me. So that's a roll over sign now. Okay, so this, and in particular, if some vector field x satisfy the condition that the along gamma t, all t, any t, then x is called parallel vector field along gamma. If then along gamma. Okay. I think so. The gamma. So this gamma is called Christoffel symbol. Or it's just called connection sometimes. Anyway, Christoffel, I think 2F. Okay. So therefore, given that, so here, and a curve. So given the connection, so Riemann manifold, actually at this moment, I didn't use anything about, so here, sorry, I didn't use anything about the metric. So far it's a metric. We don't use anywhere metric. Okay. Up to this moment, we didn't use a metric to define connection. So you can just have just smooth manifold and a curve gamma. And then you just have connection that satisfy the condition I erased now. The satisfy condition. And then given the vector field at the point x0, this is x equals 0, one can just do the parallel transport along this curve by solving this equation. So this equation dxi plus dxk dt capital X. I have to be careful. So this is the this is condition by using local coordinate. For this covariance derivative equal to 0. So by solving this equation, solving this ordinary differential equation, first order ordinary differential set of ordinary equation, one can do parallel transport along of x0 along gamma. So by solving this equation, the solution is just a parallel transform along this vector field. Okay, something like okay, maybe I should write x naught. And by solving them, you just have like this way. Okay, one can do the parallel transform along gamma. Okay. So far, we don't use anything about a metric, so we don't need to consider the Riemannian geometry at this moment. Here, I didn't use anything about the metric, but in the GR, to define a connection, you need to introduce a metric. You need to introduce a metric. So, there's a one, if you consider the Riemannian manifold. So this is Riemannian manifold. So up this moment, we don't use metric. Okay? So here, up to now, we just consider smooth manifold. And you can have lots of connections that satisfy this condition. But now, if you consider Riemannian manifold, there's a one connection that is compatible with metric G. So that's what we're going to consider. So, which is called Levi-Civita connection. Such that it satisfies the following condition. So, metric G is assignment to where? Given a two-vector field, metric will give you where? Bring you where? Function, good. So it's a function that satisfies lots of conditions: symmetry, symmetric, and also non-degenerate and positive definite. That's a metric, Riemannian metric. So therefore, this is function, and z acts on function. So x, y, z are x, y, z are the vector field. The vector field acts on function. You get what? Function. Okay, so then what we have is the condition is as follows. It's kind of Leibniz rule. So Levi-Civita connection nabla. So Levi-Civita connection nabla is just one of the connections that satisfy the condition I have written. But now we consider the Riemannian manifold. So therefore, this you can use a metric to define some condition. So this is one of the conditions. This is compatible with metric. Compatible with metric. And another condition is called symmetry or torsion free. So this is the element in vector field. So therefore, this, and also right hand side is whole element of vector field. It's a vector field. So this is called symmetric or torsion free. I prefer to use torsion free. Okay. So this is the two conditions one can impose. One can impose on a Riemannian manifold. Okay, so then the of the metric can be written as, so since gxy is a function, it's a function, so therefore one can ask the external derivative, and then in total, which set does it belong to? Which set does it belong to? Omega 1. So this is the one form. And then so the first condition can be written like this way. I think I should, yeah. Oh, did I make a mistake? Oh, I made a mistake. Sorry, you should correct me. Sorry, you should correct me. You should correct me. Sorry. So this is the correct one. You should correct me. So therefore, here, you just have assignment. So this is the one form. So therefore, I mean, just recall that the one, if you have a one form, okay, d, g, x, y. So this is one form. The acts on z is z, g, x, 1. So this is the definition of a one form. Okay, this is the definition. So this one form acts on vector field. You get this one. And here it's also treated as some one form in such a way that once you have acts on z, this acts on z, you get the right hand side. You just assign z in the below nabla. So that's what you mean. Okay. And if you use local coordinate, for second condition, it's just a symmetric. So Christopher symbol satisfy the show the symmetry between exchange of the lower two indices. Okay. And it turns out that this Levitch-Ritter connection is unique. Given the Riemann manifold, there's a unique connection that satisfies all these conditions. And then usually physicists learn the Christopher symbol as the Levitch-Ritter connection. The connection. When physicists learn the connection in GR, usually you just learn Levitch-Ritter connection. So it's just given a Riemann manifold, there's a unique connection that satisfies these conditions. And in particular, the first condition, so you can just assign, so as a physicist, you can always do the following exercise. What does it mean? What does this mean by local current? The second condition, it's easy to see, right? The second condition, maybe I should use KL. So this is, as you learn, so this is gamma KLI minus gamma I LK partial I. But of course, this is equal to the computational relation partial I, partial K, and partial L. This is equal to 0. Okay? So this is the second torsion-free condition or symmetry condition tells us. Therefore, this implies this one. Okay? Do you understand? So how do you write this first condition in terms of local coordinate? So to write the first condition in local coordinate, what you have is So this maybe so anyway, partial I G partial J partial K is partial I G J K is equal to G nabla partial I partial J K plus G del J nabla del I del K, and you just use Christopher symbol to see what's going to happen. By using Christopher symbol, so right hand side is just let's see. So this one is G gamma I J K. Oh, I should use K. L partial L K plus G del J gamma J K L. Therefore, if you apply the ordinary rule for metric, you get the oh, sorry, this is L. G. Oh my goodness, am I doing correct thing? I hope I'm doing correct thing. Sorry, this should be I. Okay, so this is the condition you need to impose. Therefore, this derivative of metric with respect to local current would lead you to the relation between connection times metric. Okay, do you understand? Do you understand? Any questions so far?
I still don't get this one. While the left-hand side is a one form, while the right-hand side is a smooth function.
So here I treat so this is Z. Sorry. So this is smooth function, right? Once one form acts on Z, you have a smooth function. So one form acts on Z, you have a smooth function. This one form acts on Z, you get this one. This is a rule. Do you understand?
That should be gamma IKL G JL.
Good. Thank you very much. You correct. Thank you very much. Yeah. Thank you very much. Good. Thank you very much. You're right. So this is the well-known relation in GR. This is actually how you define the Christopher symbol in GR. So by using the non-degeneracy of metric, one can just derive 1/2. So this is a good exercise to do. You get this one. So from here, one can get this one by using non-degeneracy. So G is invertible and so on. I mean, anyway, so we know that the derivative of the metric, you get some combination with Christopher symbol and the metric. To plug everything into here, what you will see what's going to happen. Any questions so far? Okay, so then, so definition of geodesic is the curve gamma of T in the Riemannian metric, and then if you do the parameter transform of the tangent vector on the gamma itself, you get 0. So, given the Riemannian manifold, there is a unique connection called Leibniz-Bita connection. Okay, one can define, given the connection, one can define covariance derivative along gamma. Okay, that's what we have learned. Then, so gamma is called geodesic. So in other words, sometimes I need to check the recording if it is good resolution or not. Hopefully it's okay. Okay. So in other words, so given the manifold, and there's a curve gamma, and you have a, let's use other color. You have a tangent vector point. If you do the parallel transform along number, so Leibniz-Bita. If you do the parallel transform along this gamma, you just keep having the tangent vector. Tangent vector of gamma is a parallel transport with respect to this Leibniz-Bita connection. If this is the case, this gamma is called the geodesic. So once you have Leibniz-Bita connection, and you can have for instance, you can have a bit different. For instance, one can have a bit this kind of curve. Then if you try to do, I think it's better to use the example sphere. So S2 or Sn, and you already knew, you don't know yet. Did you solve the problem? Does it have? Oh, it doesn't have. So this week you need to solve it. So you have standard metric. So you have Rn plus 1, and you can just have standard metric here. You have dxi cross dxi. So this is standard metric, and you can just pull back. You can pull back to the sphere, and you get the metric on the Riemannian metric on the sphere. And G has to be written. It's intuitively clear. S2, for instance, S2 ds is equal to as the Van Hal has written last time, this in local coordinate, the polar coordinate, like this way. Am I correct? R equals 1, yeah. So this is the S2 standard, the pullback of the local current. And with respect to this metric, for instance, geodesic is the So geodesic is, for instance, let me write a bit more clearly. It's better to draw nicely. Okay, anyway. So if you have a given 2 point, the geodesic is some, like for instance, the great circle. Geodesics can be something like a great circle, and given a 2 point, so you can easily see that the tangent vector along, if you do power transport along this metric, or you can easily, imagine it, given that this given the metric coming from the standard metric from the Euclidean metric, you can do the power transform along great circle, okay, tangent vector. Then you get, but instead, if you consider something bit strange curve, something on a sphere, something like you can consider something like this way on a sphere. Then power transport, even if you start with some tangent vector at this point, okay? Tangent vector, this is tangent at this curve. But if you do the power transport along this curve, this vector is no longer tangent to, so this is tangent to the curve, right? No longer tangent to the curve if you do the power transport. Therefore, this yellow curve is not geodesic. That's what it is. Okay. So in local coordinate, of course, given that the Levy-Stack connection, you have a unique Christopher symbol. It's a unique Christopher symbol that is computed by using metric here. Then you can just solve to get the geodesics. You have in local coordinate, you just have this one. So the local coordinate, the condition of this one, the condition d gamma dot dt is equal to 0 means in local coordinate dxi plus in local coordinate. So one can always solve this local coordinate in given the initial condition at some particular value of t. In particular value of t, so particular value of t, and one can so given the whatever, so given the Riemannian manifold and G, one can always solve this differential equation at some particular value with initial condition. For instance, if you start with point P and gamma, so this is the point P and the vector B. Let's go X, and then one can solve this equation to get the unique solution for xit locally. So one can, given the x let's see, how should we say? So the xi0 corresponds to point P, and dxi dt at point is corresponds to capital X, the tangent vector x. Then, given the initial condition, this is the initial condition, one can solve this equation for particular values, so they exist minus epsilon such that the m exists to some function or curve such that is solved. With initial condition. So that means as follows. So one can solve this equation so that one can just move a little bit along this vector field by solving this ordinary differential equation, and to get the geodesic. And why? So this condition is necessary. So only some region is necessary. For instance, if you consider a sphere as an example, okay. Since my handling of this sphere is not good, so let me try it again in here. So you have a sphere. And you start with some point. Let's go. Start with North Pole. Such that the you start with the some vector, whatever vector. So North Pole and whatever vector xp x. And one can always have. So I assume so this is S2 with metric is the standard metric on the sphere. So this is Riemannian metric, and then one can solve. So this North Pole is the initial condition P, and x is this direction, and you can solve this equation so that the geodesic is something like some great circle. Oh, sorry. So unique geodesic. Unique means this is unique. This how to say it's called quotation mark. Unique. Such that the and then you will go back. And the reason why, so as you move along t, okay, if you as you increase the value of t, so this is gamma t, so you just move along this great circle, and you hit the south pole and come back to North Pole, okay. And so therefore, if you consider 2 points along this great circle, the shorter distance is, of course, is measured by this geodesic. So this will give you shorter distance. Indeed, so this geodesic will give you the shorter distance between these 2 points locally. But as you move along t, there's another geodesic, which is just you just circle around and come back. That connect these 2 points. Okay, another geodesic. Blue one is also geodesic. and then come back to 2 points. That is not the shortest path. Okay? So the uniqueness means why you need to restrict yourself to some interval is that if you keep increasing t, there's another geodesic that connect 2 points. Okay? Therefore, uniqueness, to get the uniqueness, you need to restrict yourself some value of t. So, yeah, that's what it means. And indeed, so if you learn GR to derive this condition, so this is the equation for geodesic. So this geodesic indeed is the Euler-Lagrange equation for of this action. And indeed, this is the length. Okay, this will give you length between 2 points. Okay? So this is the action of particle that moves around in Riemann manifold MG. And since this is Euler-Lagrange equation, so this is Euler-Lagrange equation for this action S. That's how you derive in GR to obtain a geodesic. Therefore, since it's an Euler-Lagrange equation, it minimizes the action. Minimize means since this is a length, this will give a length. So therefore, so geodesic just locally gives you the shortest distance between 2 points. So this orange one is a shortest distance. I didn't write clearly about the shortest distance in the lecture. I think I should add some more explanation about that. Yep. Any questions so far? Okay. I think, anyway. I think it's a bit early, but if I talk about the curvature, I want to finish to the end about the Riemannian geometry. Let's take 10 minutes break. And I will talk about curvature from now, after the break. Let's take 10 minutes break. And please do not move this camera when you move. And if you have a question, just tell me. Oh, by the way, so I updated lecture note. So you should take a look at the updated lecture note in e-learning.
这个一直它是保护是好的，不用是那个证据，但是你要把它放这个，对，我觉得这个说法是不行的，我觉得我看不到。就是你这个很说是它为何它的艺术是它保护上就是有这样的一个，如果你这样把这件发出去，其实这个是咱们说的写到是为它。
So, if you have a metric, you can derive this derivative function uniquely. So by solving this equation. So given a metric, this equation define Christopher symbol. So locally, and the connection is equivalent to define Christopher symbol locally. So therefore, this Christopher symbol is determined by metric uniquely. So therefore, Levi-Civita connection is unique. No. So metric is given. Metric is given. So metric is given, then you can determine this Levi-Civita connection. Yeah. So there are infinite many geodesics.
数学不正呀，你写我就去把那个。
So you have to specify the body of T. For instance here, so there are infinite many geodesics. There are infinite many geodesics that satisfy this initial condition. But if you restrict the body of T, you have only the small one. You understand? Okay.
求导呀？
就是求出来它所 f 还是 x 立马值带进去还是这个
但是这种说过，你把值的那学它是一个数，但是你主要的变化会取在一个特定地址上。
就是如果是常数才可以到 r。
Okay, so shall we start? Resume. So I didn't mention, but I updated lecture note. So please take a look at the updated one. Anyway, I'm going to talk about Riemannian curvature. So now, so we just introduced. Okay, so let's recap what we have done so far. So we did. So what we have done so far is that given in this manifold, one can create so-called connection, and that is the same as locally. It's just determining gamma kij, which is delta partial I. Which is just determined by local coordinate, so Christopher symbol. And one can define, so from here, one can define the so-called notion of parallel transport along curve gamma with respect to nabla. Okay, that's what we have learned. And then also, so we can have the given of Riemannian manifold, you can have unique connection that is compatible, Lebesgue-Beta connection that is compatible metric. Okay. Then one can define the notion of geodesics. Then geodesic locally defines the distance, shortest distance. This is define the shortest distance. Between 2 points with respect to metric. Metric G. Locally. Locally is important. So as I mentioned, so in a sphere there are infinite many geodesics. You can circle around it how many times you want, okay? However many times you want. But locally to define two points, the shortest distance 2 points, there is the only unique geodesic, okay? That connect. That has a shorter distance between 2 points locally. But for instance, if you consider 2 points at north and south pole, there are infinite many great circle that connects these north and south pole. Okay, but they have the same distance. Okay? So therefore, to define the distance, a shorter distance between 2 points, the geodesics is only locally. Globally, there can be infinite many geodesics that measure the distance between 2 points. Okay. So now, so we know about the geodesic and the parallel transport. So we introduce the notion of the curvature. So the curvature is the in essence, it just so the reason why I give you the homework 1 to measure the area of a triangle is as follows. So given a sphere, you have the great circle. And now we start with some vector at this point, tangent vector at this point along this great circle. And do the paratransport. You just do the paratransport along this geodesic. And now we do the paratransport along this geodesic. And then you just do the paratransport along geodesics and then come back. Okay? So if you do the paratransform along this triangle on the sphere, at the end of the day, you don't come back original one. Okay? However, if you consider the Euclidean R2 and consider geodesics, a standard metric ds square is dx square plus dy square, standard metric. So line is a geodesic, right? Line is a geodesic. And if you do paratransport, whatever, so whatever we paratransport along this geodesics, at the end of the day, you come back original vector on R2. Therefore, this paratransport along this triangle somehow measure how this space is curved. Okay? So that's how you measure the curvature of the Riemannian manifold. And of course, this depends on how you define. So this angle here, the difference of this angle depends on how you draw. Depends on how you draw a triangle. There are lots of ways to draw a triangle on a sphere, as you already noticed in the homework 1. So this angle, difference angle, really depends on how you draw a triangle. And you will learn in homework, this homework, so that you understand what's the meaning of curvature from homework. Okay, so and to make this notion precise, you just define a curvature as the R, which is triple copy of the vector field to a vector field. And I just assign x, y, z is mapped to R, x, y, and z. That's how we write. That is defined as follows. R is nabla x, y. I think sorry. this is differential. So okay, so here I assume just assume M is just smooth and nabla is connection. M and smooth manifold. Nabla is just connection. Any connection. So any connection, given any connection, one can define the notion of curvature. Here I don't use the notion of metric. Okay. So from definition of the curvature, sorry. I think I should move to. So, from the definition of curvature tensor satisfy the following condition. This is very easy. Z is just minus R Y X Z. That's very easy, right? So once you swap X and Y, you get the minus sign. Okay. Another condition. C is the FGHRXYZ, where FGH are function. Okay. So can you check that? It's actually not so trivial. So you just need to do, what you need to do is just really, what you need to show is something like this one. It's not trivial exercise to do. Is equal to, so this is left hand side, is equal to FGHRXYZ. That's what you need to show. Do you know how to show that? This is not. Okay. Shall we add this one in the homework? Seems like no. I mean, one can check. I mean, if you want. I mean, it's tedious exercise. One has to show. One has to show. For instance, once you apply this one, you have to show this one is equal to G nabla Y H C, so that this is G Y H plus okay. So then now next you just apply this one to this one. And then you just again apply the linearity and Leibniz rule, okay, and so on. And then what you let's do okay. Let me do it. Yeah. Oh, am I doing something stupid? I think I should put C here. Okay. And also here I should put C here. Do you agree? So inside here, this is, oh my goodness, I think I missed G somehow. Yeah, I think G is everywhere. Okay. Do you agree with me or not? Do you agree? So this is the vector field, and this is function. Okay, function type vector field is vector field, and nabla acts on this one. Okay, and then you just do the Leibniz rule. I mean, to get this one. And of course, did I make a mistake? And so this part is very easy. You just swap the vector. So fx hc. Oh, did I miss h? So you should tell me. Where did I make a mistake in that case? And then what we need to do is I see. Sorry. Then I need to do it carefully. Oh, it's totally different. I mean, you should correct me. G Y H nabla X C plus next is the X H nabla Y Z plus it's. Okay, I made a huge mistake in that case. Plus H nabla X nabla Y Z. Am I correct or not? Am I correct? Do you agree with me? Yeah, I think I'm correct. This time. This time I'm correct. Yeah, I think I'm correct. Okay, so then it's okay. And you can do the same exercise for here. What you get is instead of G, Y, F, X, H, Z plus H, X, H, sorry, F, Y, Z plus Y, H, nabla X, Z plus H. Okay.
I think you missed G for the last sentence, last two terms.
Oh, you're right. You have to be careful. So therefore, here you need to use.
No. G should be the X, I think. X bracket G H.
Am I correct now? So then I choose FH and G. FH. Okay. Do you agree with that? And if you take the difference between them, what's left is, so what we want is this term, and the rest has to cancel with this one. Do you understand what I mean? Do you understand what I mean? So the rest has to cancel to get to get this one. So let's do that. Nabla fx gy hz is what? Nabla fx g y minus g y f x plus f g x y. Am I correct? Am I correct or not? Times h. Am I correct? So fx gy commutator is fxg y plus fg xy minus g y fx minus fg yx. So this is correct, right? So then you have to do the same exercise. So I'm going to erase since it's correct. Then I need to do the exercise fxg yh z plus fxg h nabla yz, that coming from here, and next is this one, minus gyf xh z plus, sorry, minus gyf h nabla xz. Okay. Do you agree? And the coming from here, next is coming from here. So next is fg nabla xy acts on hg, means the xy acts on h and z plus fgh nabla xy and z. Do you agree? So this means the and you just compare term by term. Yeah. Okay. Now I understand. Gradually understand how it cancels. So what we need is this term, and the rest of them should cancel with these terms. Okay, you understand? Oh, okay, it's a good exercise to do to check this one. It's now I can see it actually. So for instance, this fxgy cancel with this term x acts on g and yhz, right? And also x can act on here, yh by Leibniz rule. That cancel with this term, okay? And so on. And you can check, it's a good exercise to how they cancel each other. So for instance, GYH nabla XZ cancel with which one? Maybe here? Yeah. Up? Where? What did it cancel? I think it counted with this term. Yeah. It counted with this term. Sorry. And so on. I think it's a good exercise for you guys to check how it cancels. Okay. So, and this guy cancels one of this guy actually. Do you understand? So y can act on h, then you will get the f, g. So therefore you get the f, g, and cancel with this one. Okay. Some term cancel with this one, and some term is cancel with this one. And you can check they satisfy this condition. Are you okay? So it's a tedious exercise, but one has to check. I just wrote down. Okay, let's move on. I think in the final exam, I will give like this kind of computation as in one of the problem in final exam. I will this kind of yeah. So let's move on. So in local coordinate, of course, one can use always need to consider as a physicist local coordinate. So it's so assignment 3 vector to another vector. Okay. So there is 3 vector in the basis, and assignment is the. So it's a basis. So you can just have. So this vector can be written into some linear combination of this basis. That's what it means. And this is called Romanian Curvature Tensor, but not yet. I mean, this is just Curvature Tensor. Tensor of connection level. So at this moment, I didn't introduce metric G. Okay, so be careful. So I didn't use anything. I just here you can develop the theory for any connection nabla. And once you go to the the vector bundle, we can define the curvature in similar way, and you will get the so-called notion of Yang-Mills theory. Okay, so in Yang-Mills, we can define the connection in similar way, and then derive the notion of the curvature. And using curvature, one can define the Yang-Mills action. So you know you might have heard of the Yang-Mills, right? So in later, so we will define f wedge star wedge some number. So f plays a role of curvature in the vector bundle. So any which is a non-abelian version of the Maxwell theory, non-abelian version of Maxwell theory. So this theory, the reason why I developed the theory of connection curvature without introducing metric is just try to connect the Yang-Mills way. So now we try to connect. So the reason why we need to have 3. So okay, the connection is 2 vector assign another vector field. The reason why the connection needs 2 vectors is that along the curve we have a tangent vector. Okay, tangent vector along the curve. Okay. Then we want to do the power transform. Another. So another vector field. Okay. Along this curve. Okay. Along this tangent vector along the curve. Okay. Therefore, the reason why we need two vector field is that you need to do the power transform with respect to another vector. Okay, that's why we need to introduce two vector field. The reason why we need three vector field now is that we just have two copy of curve. So how to say? You just consider two family of curve in such a way that you just do the power transform as I mentioned last time, just before. If you do the power transform to the two parameter family of a curve, and we want to see the difference between them. So namely, so the Riemann tensor, you need a three copy of curve. The vector field is that we need a second derivative, two derivative with respect to curve, the two parameter family of curve. So what we have done is that given a two parameter family of curve, so let's go this direction is parameterized. So let's see x. So this direction is y, this direction is x. Okay, and the gamma is the two parameter family of the curve. So in other words, you have some segment times segment goes to manifold n, smooth map. One is x direction, the other is y direction. And you just consider two parameter family of curves. And then we just do the power transform some vector along this curve. First, along this curve, and then move it to here. So move it to So then another way to move is along this one. So there's a difference between them, okay? If you go one side and then the other side, there's a difference between orange and yellow. This difference is measured by this curvature. Okay? So the reason why you need a three copy of vector field is you just measure the difference between the power transform x lives on the third copy, along two curves, two copy of curves, okay? Two parameter family of curves, okay? That's how you measure the curvature. You know, in Nabla, it just gives you the power transform along curve. So you need one copy of curve, but you need two copy of curves to measure the curvature. Okay, and then, so what GR people study is that people study that given a Riemann manifold, so far I don't talk about any symmetric. I just introduce the Riemann manifold, and from here you have a Levi-Civita connection, unique one. Connection. Then you can just define the curvature R in the same way. Let's go Riemannian curvature. R x, y, z is delta x nabla y, z minus nabla y, nabla x, z minus x, y, and z. So this is called Riemann curvature tensor. Sometimes Riemann Christopher. Curvature tensor. And of course, so in locally, so this R Lijk can be written as oh my goodness, my notation is different from what I have written. My notation is, this is Kij, sorry. This Kij, you just plug in Kij. Just plug in here. So physicists just write down Ij. So in physicists, nabla del I is just write like this way. Okay. Physicists just write like this. Let's see. And of course, commutator of I and J is equal to what? 0. Okay. So you can forget about this time. And then you just do this exercise, the same exercise. Okay. First, you just apply this one. You get the Christopher sample, and then you do the same exercise. I mean, you just apply Leibniz rule repeatedly. I'm also become tired of this computation, but one has to do. Let's see, I think I should use, so I should use some number and you just swap J and I, okay, J and I, and take a minus. Take minus, I swap J and I indices. So this is equal to so you can just have an equation for R in terms of this Christopher sample. Okay. You understand? And that's written in lecture 2. Any questions so far? So yeah. And then, so in lecture note, I introduced some notation like it's quadrupole of the vector field. It's called quadrupole. So this is vector field, and this. Yeah. Oh, minus. Thank you very much. Yeah, you should tell me if you have noticed. So I just introduced quadruple vector field as a function. Now this is function. Okay. Since R, X, Y, Z is vector field, and this is vector field, and take inner product with respect to metric. Okay, it's a function. So then, if you apply I, J, K, L as a local field, I think my notation is horrible. My notation, I think my notation, this is K in election of L, and this is J, and here I take as I. This is my notation in election node. And then if you plug this one in, this is R I, J, K, L, R, S, J, K, L, G, S, I. Seems like this is my notation. This is my notation. Yeah. Any questions so far? And then once you do the it's very, very tedious, but this is the one can show the following identity. So this curvature tensor satisfies the following condition. So first one is very easy. How do you show this one? Is it easy to see that? Why this is true? What? Can you speak up? Yeah, so this is definition, this one, once you swap x and y, you just get the minus sign, okay? R, X, Y, Z, W is equal to minus WZ. This is not that straightforward. Yeah, not that straightforward. One has to use the metric compatibility and so on. I mean, it's always a good idea to use the definition of Christoffel symbol or Lebesgue-Witte connection. So you need to use the Lebesgue-Witte connection property, Lebesgue-Witte connection. But in fact, this will be the exercise for you to show all the identity. So this property and another one, you have to use all the property of the I mean, mathematician would like to write everything in coordinate-free way. So if you use all the property of the curvature, Lebesgue-Witte connection, and the curvature definition of curvature, one can show everything of this identity. Okay. And And then this will be the homework for next homework, the exercise, one of the problems. So I'm not gonna derive. So in particular, the last two are called Bianchi identity. So last two are called Bianchi identity. And in lecture note, I have written down in local current what it means. But I'm not gonna write down the local current. It's just a tedious. It's just a repetition I'm going to avoid. Any questions so far? Yes. So yeah. So now I can just define. So Ricci curvature tensor in such a way that the Rij is just a contraction of the indices. So this is the curvature tensor. This is just if you use the Riemannian tensor. In particular, Rij is proportional to Gij, and this is called Einstein Manifold. Mg is called Einstein Manifold. Can you give me some example for Einstein Manifold? What is the Einstein Manifold? Can you give me some example for Einstein Manifold? I'm sorry?
The universe with only with
Only with what? Dark energy? Dark energy. Good. But can you give me? That's also right answer. But I wanna hear some other answer. Huh? Speak up.
like projective space.
Projective space. You mean RP? Huh? You mean? CP1. CP1 is S2. CP1 is S2. Fubini-Studi metric. Okay. Good. But Fubini-Studi metric is the same as the is it same as standard metric on S2?
It's the pullback of standard metric.
Standard metric, pullback of standard metric of R3, right?
I think so.
Yeah, I think so. Yeah. So in fact, the S2 with the standard metric G is actually Einstein manifold. You can check today's exercise. Today's homework. You can check. And more simpler example. Give me a simpler example. Flat space. Flat space. Flat space S2. Most of the anyway. Okay, so that's enough at this moment. And also one can just contract one more. So if this is then one can also scalar curvature. R is just a Gij, Rij. So this is scalar curvature. R. Okay. So now we're ready to connect the Gauss-Bonnet Theorem. So what Gauss has found in the study of surface, he's a great mathematician, one of the greatest mathematicians in the history of human being. And also, he's also a physicist. That's why he also studied electromagnetism. And also, he introduced some notion of geometry that goes beyond this Euclidean geometry. Anyway, so if you have chance to look at the Gauss collective paper, there's a huge collective paper by the Gauss. It's better to take a look at it. He did lots of computation, and very, very precise computation, and he did lots of contribution to every area of mathematics: number theory, geometry, analysis, differential equation. Also, he made a contribution to the electromagnetism and physics, as you know, Gauss law and so on. If you have chance, go to the library and take a look at open the Gauss collective paper and see what he does. He did amazing. It's written it's written some the German and also Greek, but it's hard to read the language. But he did lots of computation. You can read off the computation, and it's amazing. You can see that's the work of the genius. You can see the genius work. So if you have chance, you should take a look at the Gauss collective paper. It's a huge volume, but just open one of them. So what Gauss has found as follows. So they find the Gauss curvature is on a surface. So the sigma and the g is the oriented cross surface or Riemann surface. It's called oriented cross surface. In other words, cross two-dimensional manifold. It's often called Riemann surface. Then one can define curvature tensor. Now we have only two directions, right? Locally. So 1, 2, 1, 2. So 1, 2, 1, 2. Okay. And you can just take determinant of G. So that's the Gauss curvature one can define. Then what you get is as follows. So this is Gauss-Bonnet Theorem. It's called Gauss-Bonnet Theorem. So left-hand side depends on choice of metric. Okay, left-hand side depends on choice of metric. Curvature depends on choice of metric. So therefore, whatever. So in Euclidean geometry, you can embed Riemann surface in any way. So you can just embed the Riemann surface anyway. So you can just smooth. If it is smooth enough, one can just do lots of deformation and obtain the Probach metric. Okay. So then they have different curvature at the point. Okay. However, once you integrate out all the Gauss curvature, what you get, right-hand side is independent of the choice of metric. It's a topological quantity, or a characteristic. So therefore, this Gauss-Bonnet theorem would connect differential geometry, left-hand side differential geometry. You need to have a Riemannian metric. You need to introduce metric. But right-hand side is topological object. So Gauss-Bonnet theorem connects two branches of two subjects in mathematics. One is left-hand side is differential geometry, right-hand side is topology. That's a that's a very deep theorem, and it's a similar. Anyway, so this was first found by Gauss and Bonnet formulate by using curvature, and now then Chern tried to understand the higher dimensional version of Gauss-Bonnet Theorem. So I think his name. Is this the right way to write? No. Oh my goodness. Can you? Oh my goodness. I should. Oh yeah, it's a. Yeah. Can you write down the Chan? Yeah. Sorry, I should. Okay, so I should. So he's one of the most famous Chinese mathematicians. He tried to formulate. Chen has tried to formulate the Gauss-Bonnet theorem in higher dimensional Riemann manifold, and he introduced so-called chunk class. And that's called characteristic classes and so on. But that's what we're going to learn from later. And the Euler class and also anyway, that's called characteristic classes. And after the many so after the similar thing is called Riemann log. And also this was generalized by so-called Hirzberg and Grothendieck. And also Grothendieck. So Riemann log is just a theorem for Riemann surface as a complex manifold. But Hirzberg generalized to the anyway. But I will explain the four-dimensional manifold by using signature and so on. But anyways, and so one can generalize to the so-called double cohomology and so on. And Grothendieck used to translate everything in terms of language or category. It's a deep theorem, and if you use this one, so-called Additive, in analytical word, you leads to Additive finger and both part of the so-called index theorem. So this is the complex geometry. So this is really a complex geometry. And also like a sheaf algebraic geometry. And here it's more analytic. It's called index theorem. So left-hand side is indeed depends on metric, but moreover it's a local. Kappa, as you can see, is just a kappa at a point. Is you find a curvature at a point. It's a local object. But however, once you integrate a local object, whole manifold, you get some topological information. Okay, that is only encoded information, global information. So therefore, Gauss-Bonnet theorem is the first theorem that connects from local quantity to global topological information. And this theorem is very important, and then many people has generalized, and then one of the slogan in mathematics. One is local to global. Okay? The other is connect two different areas of mathematics. So a single bot or Patodi index theorem is just connect analytical word and also topological word. Okay. And also it also involves differential geometry and so on. But this index theorem plays a very important role to compute anomaly in quantum field theory. Complex geometry, Riemann-Loch is also coming from Schiff, or whatever, Schiff cohomology or complex double cohomology is just some construction for local object. But once you integrate out this so-called, that's also index. I mean, anyway, index of double cohomology, you get the Euler character of double cohomology and so on. Yeah. So one motto is one slogan is local to global, and the other is to connect two different area of mathematics. These are the very, very important theorem in mathematics, and that is often used in physics. So now let's move on to Einstein. Did I? Okay. Any questions so far? Oh, I thought of, I may go to simplex geometry today, but I think I won't go. I'm not sure. Let's see. So once you start with the action, which is the so this is the action. So R is a scalar curvature. The gamma is the cosmological constant. And then Lm is Lagrangian for other field. It can be anything. So electromagnetism, whatever. It can be anything. Some matter and so on. That's what it matter. So Einstein, this is called Einstein hybrid action. Here, so metric or curvature is of space-time is now a dynamic object. And if you take variation with respect to delta G mu nu is equal to 0. Okay? So now metric is dynamic object. So this is the Euler-Lagrange equation for this action. And what you will get is the exercise. So what you will get this one. T mu nu is a stress and energy tensor coming from Li. So Sm is just a square root G d4x Lm. And if you take the variation with respect to G mu nu, you get the T mu nu up to some constant. I don't remember. So this is the Euler-Lagrange equation for this Einstein hybrid action, and this is the famous one of the most famous equation in physics called Einstein Equation. So this is what it means that so right hand side is the stress energy tensor. Okay. So right hand side is stress energy tensor. Is left hand side determines is the information equals the curvature of the space time. So therefore, this equation means that the energy or stress energy tensor would determine the curvature of the spacetime, roughly speaking. So, and also, as you already know, so this R mu nu is the second derivative of the Riemannian metric, and also it's nonlinear. So it's hard to solve, but there are some cases you can solve analytically. So one is the most famous case is called what? Schwarzschild. So Schwarzschild. Schwarzschild. So that's 1 year after the Einstein discovery of Einstein equation. So Einstein equation 1915, Schwarzschild solution was found in 1916. Okay. And also, so you have to impose Schwarzschild. You have to impose static and striker symmetry to solve. So highly symmetric situation one can solve analytically. And some situation one can solve analytically for black hole, carbon hole, and so on. I think did Eden already derive this equation in the GR? Did he derive Einstein equation? Not yet. Oh, okay. He talks about the Riemannian geometry in that case still, I guess. Okay. I mean, originally Einstein didn't derive as the equation motion of this one, but anyway. He derived physicist way to derive this one. So as most of you know, right? Equivalence principle and Riemann geometry and stuff like that. So that's and then the reason why that one is Einstein manifold is as follows. The reason why that one is called Einstein manifold is that suppose there's no matters in the universe or space-time. The right-hand side is 0, okay? And if Einstein manifold, the space-time is the Einstein manifold, so then R mu nu is some proportion to lambda g mu nu. Therefore, if you take the contraction R is equal to 4 lambda. Do you agree? Do you agree? 4 lambda. If you contract with g mu nu, okay? And plug back into here, so R mu nu lambda g mu nu minus 1/2 4 lambda g mu nu plus lambda g mu nu is equal to 0. If the space-time doesn't have matter, okay, anything, it's just only cosmological constant, then what you will get is, when lambda is equal to capital lambda, this is the solution. Do you agree? Okay. So therefore, it's a solution for Einstein equation with no matter, but with cosmological constant. Do you know some of them, except this sphere and so on? The solution of this equation. Have you ever heard of something? Huh? What? So the most famous one is Dozita space. Or sometimes some amazing anti-Dozita space. Have you learned this one in cosmology? Yeah, so for instance, ADS-CFT, you might have heard of it, ADS-CFT. Gravity on ADS space is equivalent to CFT at large n and so on. So, but anyway, so the anti-Dozita or the Dozita space is the solution of the the empty space-time with cosmological. If lambda is positive, which means dot zeta, positive is dot zeta, and the negative is under dot zeta, right? Okay. That's what. Oh, but it's quite strange. I mean, here at Fudan, there are many people who teach GR and the cosmology, right? Antonino, Cosimo, and Eden teach GR and so on. You guys should know. Didn't they teach this stuff? Dot zeta or under dot zeta space in cosmology and so on? No. That's very strange. Anyway, if you want, open one of the book, Weinberg or something, whatever, of the book, you will learn something. Okay. So to see, so in this one, locally, G mu nu, locally, at the point, you can always have minus 1, 1, 1, 1, okay? So at the point. So in other words, so I choose Minkowski metric, Minkowski signature for metric in physics, in space-time. At the point, always you can take diagonal matrix minus 1, 1, 1. So this is called white in physics. And always you can choose a local coordinate in such a way that the metric is always minus 1, 1, 1, 1. What is it called in physics? Huh? I'm sorry? No. There is a physics. That's how the Einstein derived the GR.
Local inertial system.
Yeah. So this is.
Local Riemann.
Yeah, I mean, of course, locally you can. So this is called. The first principle Einstein derived this equation. What is it called?
Equivalence.
Yeah, principal equivalence. Okay. That's how Einstein derived. So always at the locally you can just have a flat space. Okay. That's a. So that, and I took Minkowski signature, and then. So as I mentioned, as I already erased, if you have a geodesics. So maybe so this R, curvature R, appears so-called the how this. So if you consider gamma, I think I made a notational conflict. But anyway, so if you consider two-parameter family of geodesics in Minkowski signature R 1,3, 1,3. And this is a time-like geodesics, okay? Time-like geodesics, and this direction is t, and this is spatial one, s, okay? Let's consider such a situation. And this one, this t direction is geodesic, okay? Geodesic, and then. Oh, by the way, so before I erase, so it's local to, as I mentioned, local to the global. Poincare-Hopf theorem is one of them. So you just count the number of the index of the zero of the vector field, you get the Euler characteristic. So Poincare-Hopf is also the connect local to the global. So local means the zero of the vector field is a really local object. But if you sum all the index of the zero of the vector field, you get the overall characteristic. That's global object. So Poincare-Hopper is also one. Before this. So let's define the local. So the physicists always like to write everything in local coordinate way. So let's consider Ti is equal to partial xi, t and xi is equal to, let's consider s. So what I meant is that this tangent vector here is Ti, partial I, and this tangent vector here is xi. Okay. So then, by definition, so you can always, by definition, Ti partial I and also xj partial j always commute because, always commute. Yeah, because of course partial Ti, partial dou. Oh my goodness, I made a mistake in there a typo in the election. I just added this one yesterday. So that leads to this commutation relation. So therefore, if you use the Levi-Civita connection, as you remember, so torsion free or symmetry will tell us that the and what we are interested in that is some acceleration of this spatial metric, spatial vector. So this is spatial vector, and we would like to understand acceleration along dt square. I'm sorry, there are lots of typo in the lecture. I'm sorry. I need to correct it. So I would like to understand acceleration. So in Newtonian equation, so x double dot is equal to fa, right? So this is Newtonian equation. So this is acceleration. So second derivative acceleration. I want to understand acceleration along this. So along this geodesic, time-like geodesic of the spatial vector. Then I just write down the computation. You can just follow. I don't have. Okay, I have enough time. I don't think I can. I don't need to go into Simplex geometry today. So let's finish Riemann geometry. So one can use this one. You can apply this relation into here. Okay. Not okay. Xj. So Ti, then you just apply the Leibniz rule. I'm a little bit tired, but anyway, Tk, number k, xj. I just apply Leibniz rule. So I just apply this one into Leibniz rule using Leibniz rule. And then again, I use this relation to rewrite everything. And also I introduce curvature curvature tensor, Riemann curvature tensor, such that the xk delta k tj j ti plus xj tk nabla j nabla k ti plus r I a sorry d Why I use DCB? Sorry, I think I made a stupid mistake. Yeah, I think it should be LI, LKJ. Sorry, there are lots of typo in the lecture. I will correct right after the lecture. Okay, and then, and this is equal to. So first one, I use apply this one into here, and also I use Riemann curvature is essentially, yeah. So this part is equal to this part, okay. And then xk, nabla k, tj, nabla j, ti. So I just rewrite everything by using Laplace rule. Again, it should be the typo in the lecture note. And since this is t is a geodesic, so this one is 0. This one is 0. If it is geodesic, this one is 0. At the end of the day, what you get is r, I, lk, j, xj, tk. So that's how you derive acceleration of this spatial vector along this time-like geodesic. And this is called, do you know what it's called? So this is called tidal force. So once you move whatever, free falling to black ball, you will see tidal force. Your body will be distorted, okay, due to the curvature of the black hole. Once you move into the black hole, whatever. Have you ever watched the Interstellar? Interstellar also depicts how the tidal force is. So once you go into the black hole, you see huge tidal force due to the curvature. That is the acceleration of the spatial vector, second derivative of the acceleration along time-like vector. So the curvature itself, or curvature of space-time, becomes dynamical object in Einstein theory of gravity, and you feel once you go to the anyway. Space-time with like a high curvature density. Okay, so this is the end of Riemann geometry, and next week I will move on to simplex geometry. So in the first lecture, I briefly introduced this simplex manifold. The order is a bit different. I already explained briefly Einstein theory of general relativity. But the simplex geometry is closely related to classical mechanics. And then next week I will talk about the classical mechanics and simplex geometry. Just the introduction. Simplex geometry is very difficult. Personally, I work as a research subject as a simplex geometry and physics, but it's a very difficult object. And sometimes in physics it's called A model, topological twisted A model. And it's a very deep subject in simplex geometry. And it appears in also the string theory. We will see the beginning of simplex geometry next week. Okay, so if you have a question, just tell me. Let's finish.